Some of the most challenging structure steel welding and inspection problems are encountered during the construction of round tubular members, especially at the TKY node connections. Often these are not primary load carrying structures or they have limited structural functions. Nevertheless, in the offshore industry, tubular TKY constructions is used as a primary load path for the structures such as fixed offshore platforms. The jacket of an offshore structure is made up of tubular members. These tubular members are made up of a steel and designed to resist yield and buckling loads. The tubular sections from various type of joints like T joints, K joints and Y joints. In addition to the weight of structures and equipment, these joints are subjected to operational and extreme cyclic loading conditions resulting from normal winds and wave actions or earthquake, hurricanes, vibration of equipments, extreme cold, due to which fatigue failure starts and increase as the time passes. Loads are therefore either static or cyclic, and the quality of structural welding for tubular connections must endure for the design life of the structure. Worldwide, various code standards and recommended practice are used for the design, fabrication, welding, and inspection of TKY joints, such as AWS T1.1, ISO 19902, API RP2, and DNV RP C203. Even cursory review of code requirements for tubular welding and inspections reveals that tubular node connections are made complex than the flat plate structure steels. Thorough planning, training of all phases of the structural tubular fabrication project will help to avoid necessary problems and therefore maximum productions and minimize reworks and repair. This presentation focuses on the fit-up and weld visual inspection of tubular TKY joints with objective of emphasizing the need for the planning. Overview of concept related to TKY joint configuration. Just imagine two box hollow sections intersecting at 90 degrees angle as shown in the picture. If both sections are the same size, the local angle at the side indicated by the arrow will be 90 degree, while the other two sides will have a local angle of 180 degrees. Here it is important to note that even though the overall intersection angle is 90 degree, the local angle at the weld configuration change based on the specific location. Similarly, let's see some more pictures. By examining this picture, it becomes clear the distributions of acting stresses is influenced by the local angle, regardless of overall intersecting angles of the brace or structural member. For instance, even if the section intersected at 90 degree as we had seen in the picture, the stress concentration will be different between the localized areas with 90 degrees and 180 degrees. In simple words, we can say the way stress will be concentrated on area where a local angle is being formed as a 90 degree and the area where the local angle is being formed as 180 degree will be totally different. Now just consider replacing this box section with the circular tubular section. Since intersecting sections are circular, the bevel angle and localized dihedral angle will be vary along the weld lines in relation to the local angle formed between the cord and the braces. In case of box hollow sections, we hardly have 2, 3 or 4 area where the angle is being changed, but in circular all around the weld line there is a possibility the angle change. That is subject to the size of cord and the brace and also the intersecting angles. Explanation of fundamentals of TKY weld joints. Here we have the pipe tubular which needs to be cut to the specific dimensions required to create a brace angle according to the construction drawing. Here is an actual picture of a node brace stub. As you can see here, the plane view of the cut section, it has an oval shape appearance. When this stub is connected to the code, another tubular member, the resulting node connections can be divided into three key areas. Heel. This refers to the area where the stub connects to the main structure and form brace angle, providing support and stability. Sides or saddles. These are the portions of the node connection that surrounds the stub and help the distribution of the load evenly. Typically, these are the curved sections on either side of the heel. Toe. The toe is the end section of the node connections where the stub tapers off. This is the point at the opposite end of the heel area. By understanding these three major areas, we can ensure proper fabrication and installation of the node brace stubs, resulting in a strong and a reliable connection. Extract of AWS D1.1 denoting different part of tubular nodes structure. Local dihedral angle. At the top left, the definition of the local dihedral angle is provided. To better understand it, let's break down the definition. Let's focus on the underlined text and illustrate it on the node tubular connection figure. The underlined text states the angle measured in a plane perpendicular to the line of the weld. The white line represents the line of the weld. Now let's read the blue and the yellow highlighted text together, which states a plane perpendicular to the line of the weld. To better understand it, the points are marked at the various locations on the weld line. By placing a set square with a right angle on the weld line, aligning the base of the square with the weld line, we can then draw a perpendicular to the line of the weld. At the center of the heel area, the dihedral angle is equal to the brace angle. For instance, if your brace is 30 degrees, the dihedral angle will be 30 degrees at the heel area. It is important to note that the heel is always considered to the starting point for the zone marking for weld size with respect to the dihedral angle. Similarly, at the center line, the dihedral angle on the toe is 180 minus the brace angle. For example, if the brace angle is 30 degrees, then the local dihedral angle will be 150 degrees at the toe. Let's further dissect the definition. The next underlined text states between the tangent to the outside surface of the tube, cord and stub being joined at the weld. Focus on the word tangents. Before exploring further, carefully examine the perpendicularly marked white lines on the weld line. Some of the line extended on the cord forms a circle. With reference to these circles, the tangents need to be identified to measure the local dihedral angle. Let's continue exploring the remaining part of the definition. The green highlighted and underlined text. The exterior dihedral angle, where one looks at localized section of the connection such that the intersecting surfaces may be treated as planes. Both surfaces are to be treated as a planes, but in the given section the stub appears as a plane, whereas the cord is a curved surface, not a plane. Therefore, as per second line of the definition, it is necessary to identify tangent. No. Extend the plane of the stub onto the cord, then draw a straight tangent touching the intersecting point between the stub and the cord. A tangent is a straight line or a plane that touches a curved or curved surface at a point, but if extended does not cross it at that point. The angle measurement between these two planes will be the local dihedral angle. Note: it is not necessary for the intersecting exterior surfaces to always be curved. In some instances, both surfaces can be straight planes, such as in heel area or the toe or some other zones depending on the localized configuration. In these cases, the angle measured between the planes is the local dihedral angle. In other instances, as shown in illustration, one or both intersecting surfaces can be curved. In these instances, tangent need to be identified to measure the local dihedral angle. Now, I will briefly talk over the remaining elements of weld joint. First is bevel angle. Bevel angle is angle between the bevel of a joint members. In case of TKY weld, the bevel vary with respect to the dihedral angle at various zones. Root opening is a separation at the joint root. TW required is a required weld size as per drawing or construction code or standard. The TW actual is an actual achieved weld size after welding. Zone marking, local dihedral marking on job. There are two methods for performing the zone marking or distributing the area per dihedral angle wise on the node tubular weld joints. Number 1, using the degree protector or counter profile gauge. Number 2, applying graphical depiction provided in AWS D1.1 Annexure 2. Before we start, let's briefly discuss why zone marking is required. Earlier it was discussed that the stress acting concentration is subject to the localized angle between the intersecting planes. Therefore, various code and standards specify required weld size and weld profile based on the local dihedral angle. The extract of ISO 19902 shown here denotes weld size as per the given range of dihedral angle. This range can be called a zone. So to ensure the distribution of the weld at various locations of node connection, it is deemed necessary to do the zone marking and specify the required weld size on different portions. For the purpose of this video, I will name them zone 1, 2, 3 and 4 sequentially. The first method involves physically checking the local dihedral angle at the desired point to find out the zone per local dihedral angle range. First measure the outside circumference of the stub. Divide the measured circumference into equal parts as deemed necessary. This is totally depend on your estimations. It can be judged whether 8, 12 or even more or fewer divisions are required. I normally divided the circumference into 8 equal parts. Extend the divided parts line to the line of the weld. Remember, the center line at heel area will be considered as the initiation point of marking. At the heel area, the brace angle is equal to the dihedral angle. So assuming the brace angle is 30 degree, then this area will be in zone 4 and the required weld size will be 1.75 times the brace stub thickness. Draw a perpendicular on the line of the weld using a right angle set square. At the center on the toe area, the dihedral angle will be 180 minus the brace angle. Here the assumed brace angle is 30 degree, so the dihedral angle at the toe will be 150, which falls under zone 1. Continue marking perpendicular to the line of weld. Before continuing further, just observe how the drawn perpendicular lines keep changing along with the weld line of the weld. Let's zoom in to have a closer look at the different areas of the tubular connection. Now by using the degree protector or counter profile mimic gauge, the local dihedral angle can be found out. The degree protector or counter profile mimic gauge should be placed exactly on the drawn perpendicular lines. To make it easier to comprehend the whole concept I have created an animated sketch parallel to the picture. Graphical explanation of local dihedral angle for tubular TKY node weld connections. For zone marking, only one half side of stub needs to be marked, as it will be a replica of other half. This is important to remember when determining the local dihedral angle. The red circle represents the stub diameter, blue line represents the dihedral angle. Let's create a graph to understand the correlation between the stub radius, chord radius and a resulting local dihedral angle. The red horizontal line represents the brace radius and the blue vertical line represents the local dihedral angle. Both lines should be divided equally up to 180 degrees. Since the brace angle is 20 degree, the starting local dihedral angle from the heel area will be 20 degrees. There are multiple curves with the function values from 0.2 to 1 on graph. Each curve is based on the value of a function beta determined by the ratio of stub and chord radius. Assuming the chord diameter is 2000 mm, R 2000 divided by 2 equal to 1000 and the brace diameter is 1000 mm, the R equal to 1000 divided by 2 500 mm. So the beta will be R small divided by R capital 500 divided by 1000 resulting in a value of 0.5. Measure the circumference of stub, divide the resulting circumference by 360 to obtain 1 degree value. The local dihedral angle range of 35 degrees downward will fall into zone 4. Now that we knew the brace angle and the dihedral angle are equal at the heel area, let's find the related brace parameter angle division for the 35 degrees dihedral angle. Mark the point at 35 and extend the line until it touch to the 0.5 factor curve. The further the line is to be dropped vertically on the base. At this point we have a 21 degree parameter divisions on the stub. Multiply the obtained degree by 1 degree value of 8.726 mm. So up to 183.24 mm on both sides of heel area will be zone 4 and the weld size shall be 1.75 times the brace thickness. For zone 3 we have a range of 35 to 50 degrees. So now the parameter division of the stub for a 50 degree dihedral angle is to found out. The resulting parameter division is 32.5 degrees. From zone 4, 100.5 mm on both sides will be zone 3. The required weld size should be 1.5 times the brace thickness. For zone 2, the range is between 50 to 135 degrees. For 135 degree dihedral angle, the parameter divisions will be 108 degrees. Accordingly, 659 mm on both sides from zone 3 will be zone 2, and the required weld size for this zone is 1.25 times the brace thickness. Zone 1, from 135 degrees and over, it falls under zone 1. We know that at the toe the local dihedral angle is equal to 180 minus brace angle. Here the brace angle is 20 degrees, so concluded dihedral angle is 160. The 628 mm from zone 2 on both sides will be zone 1, and the required weld size and the weld profile are to continue the line of the brace stub, except that the transition width need not to exceed 1.75 times the brace or the thickness. Additionally, in this zone a smooth profile is required between the brace and the code weld. In following slides, the graphs are given for the different brace angles. How to take weld profile using counter profile gauge. Perpendicular to the weld. Draw a line where the gauge is placed using marble chalk. Ensure all wires of the mimic gauge are properly set on the weld profile. Draw profile with a pencil on a paper. Then take the profile of the code curve with the mimic gauge. Transfer and extend the curve of the initial taken profile onto the profile sketch. Add the thickness of the stub in the sketch and extend the lines towards the code curve. Ensure the root gap is maintained in the profile. The exterior line of the stub thickness until it touches the curve. Note that in accordance with the local dihedral angle definition specified in AWS D1.1, the local dihedral angle is to measure on the exterior surface. This is the way the profile sketch line is being extended. To mark the point, to draw a tangent line. Ensure the tangent line is straight at 90 degrees to the radius of the curve and does not cross it if extended. Another example of profile is where both intersecting surfaces are straight planes, not radially curved surfaces. Weld size with respect to local dihedral angle. Extract from ISO 19902 defines key constituents of no TKY weld joints. Following slides contain typical weld profile taken from a standard drawing used for fabrication and welding of TKY weld joints.